I am going to talk through these slides about how to draw Lewis structures with multiple bonds and also how to draw resonance structures. All right, so I'm sorry that I'm out today. I've got some car issues. So your task is turn in the homework. A lot of you already turned it in last class. That was the single sheet of paper about Lewis structures. And then there's a couple notes to take along with these slides. All right, definitely you'll need your periodic table. You'll need to be adding up valence electrons. So you need to be able to easily see the group of the elements. All right, here's our task for today. And you do have homework. It is on Canvas. It's a 10 question Canvas assignment. You've got 2 attempts on it and it's due at the start of class. All right, so the topic for today is Lewis structures, but this is with things with multiple bonds and something called resonance. All right, so go ahead, write that title down. All right, so before I get started, I want you guys to be familiar also with this little shortcut that is sometimes referred to as HONK 1234. So what this means is that there are some patterns, and you've already seen this with your single bond Lewis structure drawings. We have seen already that hydrogen likes to have just one bond, right? It only has one valence electron. So to get its duet, it's going to just form one bond and then it's done. When we have nitrogen and anything else in group 5A, so phosphorus as well, it has 5 valence electrons and 3 that are unpaired. 3 that are unpaired, right? So I'm going to highlight those in blue. So nitrogen will tend to form 3 bonds, and then we'll have 2 non-bonding electrons just on the atom. All right, oxygen has 6 valence electrons. It has 2 that are unpaired, highlighted in blue. So it tends to have 2 bonds, and then we'll have 4 non-bonding electrons. All right, you could also refer to that as 2 lone pairs or 2 non-bonding pairs of electrons. All right, and then carbon has 4 valence electrons, and carbon likes to form 4 bonds. It does not often have non-bonding electrons on the atom. It's pretty much all its spots are occupied with bonds. All right, so just remember that if you're sometimes having trouble making a structure, that's a good kind of rule to go by. Now, it is not perfect. There are, of course, exceptions, but that's a good starting rule. All right, so these are just some pictures. All right, if you want to add in your notes, hydrogen likes to form 1 bond. All right, so I'll just circle some hydrogens that have 1 bond. All right, so the hydrogen and water. All right, the hydrogen here in NH3, just 1 bond. Hydrogen here in CH4. Hydrogen when it's bonded to itself, right, H2. Hydrogen and hydrogen monochloride. And even in slightly more complicated molecules, here all the hydrogens have just 1 bond. All right, oxygen likes to form 2 bonds. So just to see that, here is an oxygen that has 2 bonds, and that is something we're going to look at today called a double bond. All right, it's got these 2 non-bonding electron pairs and then 2 bonded electron pairs. All right, we see that as well in this O2 molecule. You'll learn how to draw that today. All right, but it's got 2 bonds. So here I'm pointing to them, and then it's 2 non-bonding pairs. All right, over here we have water, and you can see it has also 2 bonds. So here's 1, here's 2, and then it's 2 non-bonding pairs. And even over here, this is formaldehyde. We've got 2 bonds, 2 lines and a double bond, and then 2 non-bonding pairs. Now, like I said, there are exceptions. Carbon monoxide over here, this has 3 bonds to oxygen and 1 non-bonding pair. This is ozone or O3, and you'll see the center oxygen has 3 bonds, so 3 altogether, and then a non-bonding pair. And then one of the terminal oxygens has 2 bonds, and then one has 1. So there are definitely some exceptions, but 2 is a kind of like a natural state for oxygen. All right, nitrogen likes to form 3 bonds. Here's nitrogen with 3 single bonds. Here's another nitrogen with 3 single bonds. Here's a nitrogen with 2, a double bond and a single bond, all right, but still the non-bonding pair on the atom. All right, a nitrogen with a triple bond over here still has one non-bonding pair, and then nitrogen again with a triple bond. All right, and then that leaves carbon. Carbon loves to have 4 bonds. So in the CO2 molecule, carbon has 1, 2, 3, 4 lines coming out of it, so 2 double bonds. All right, this one also has 4, a double bond and 2 single bonds. You could have 4 single bonds. You could have a triple and a single bond, but like we saw before, there can be some exceptions. All right, so that carbon has a triple bond. Okay, so a lot of those that I showed you have more than single bonds, right? We have like 2 lines or 3 lines together. So some molecules do not have enough valence electrons to only have single bonds. So they have to create more shared pairs of electrons, or double and triple bonds. Double and triple bonds. All right, so just like a single bond is 2 electrons, a double bond is 4, right? You can kind of imagine that the electrons, you can draw them on the ends of the lines there. All right, and a triple bond has 6, right? Each line has 2, 1, 2, 3, 4, 5, 6. And that is how we represent a set of 6 shared electrons, or 3 shared pairs. All right, so you are going to make double and triple bonds when you're drawing a molecule and you run out of valence electrons before everything has an octet. All right, so you'll have to move a couple electrons around to be in between the 2 atoms. All right, so let's start with a picture of carbon dioxide. All right, carbon dioxide, we know its formula from its name here. CO2, right? 1 carbon, 2 oxygens. All right, we're going to start the same way. We're going to count up all those valence electrons, right? Carbon has 4, oxygen each have 6. All right, so I add that all together. Let's see, what is that? 16? All right, so we have 16 valence electrons. All right, so same step as before. All right, next we're going to figure out who goes in the middle. All right, so I told you guys that's who we either have 1 of or the least electronegative one, so that's carbon. All right, we're going to put our oxygens left and right and connect them with our single bonds. So remember, we're using up those 16 electrons. So we used 1, 2, 3, 4. All right, so I'm going to keep track over here. So I'm down to 12. Okay, so now I'm going to sprinkle those 12 around until I give everyone an octet or until I run out. All right, try to do this kind of symmetrically. I start on the outside. So I'm going to go 1, 2, 3, 4, 5, 6. Okay, so we're down to 6 now. And then 1, 2, 3, 4, 5, 6. Okay, so we have run out, but hopefully you see, and I'll circle this in blue, that the carbon here does not have an octet yet, right? The oxygens are doing okay, right? The oxygens have their octet, but carbon does not. Carbon only has 4. Okay, so in this circumstance, we're just going to kind of move a pair of electrons over so that it's in between the oxygen and the carbon. So I kind of think of it as like who is oxygen rich and who is oxygen poor, and we're going to steal from the rich. So our oxygens have the octet. So we're going to take a pair and put it now in between the oxygen and the carbon. All right, so I'm going to redraw an intermediate. All right, so now I've got 2 lines here, carbon, oxygen. All right, so we're almost there. Now this carbon in the middle has 1, 2, 3, 4, 5, 6 electrons around it. So we're not quite done. So let's move another pair from the other side. All right, and then we'll get oxygen, 1, 2, 3, 4. 1, 2, 3, 4. All right, and then that is our final molecule. All right, your pairs of electrons on your oxygens, they can be on the top and on the bottom. It doesn't totally matter, but that is where mine ended up. All right, so a key thing students sometimes make a mistake is they keep adding electrons even though they've already run out, they've already placed them all. So I think it's good to go back and check, like, do I have 16 electrons? All right, let's count those. I'll count them in purple. Got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, yep, I have 16. All right, does everyone have an octet? All right, I'll just count. So here is oxygen's octet, same on the other side, and here is carbon's octet. All right, so that is a commonly drawn molecule of CO2, carbon dioxide. All right, let's try another one. All right, let's do molecular nitrogen. Molecular nitrogen. All right, so you guys know when you hear the words molecular something, that means I'm probably talking about a diatomic. So that is N2. All right, so valence electrons, if I'm counting those up, I just have 2 nitrogens. All right, take a moment, find how many valence electrons nitrogen has. All right, you should see they each have 5. Add that up for 10. All right, so we have just 2 atoms here, so just nitrogen and nitrogen. So we're going to start by bonding them together. All right, so that took up 2 electrons, so I'm down to 8. All right, so again, I like to sprinkle things around kind of symmetrically. 1, 2, 3, 4, 5, 6, 7, 8. All right, so I'm down to 0. Okay, so I cannot add any more dots. I can just move them around. All right, so does anything have an octet? No. All right, if I circle around this nitrogen, right, it only has 6 electrons around it. This one likewise has 6. Okay, so they both need to share to get their octet. They both do not yet have an octet. So I am going to take one pair and scoot it down. All right, and I'm doing this kind of slow to begin with, but eventually you'll start being able to see. All right, so this one, here we go, here we go. All right, so what did I fix? Well, the one on the left still does not have an octet, right? It still has 6. But the one on the right, now it has an octet. Okay, so how do we fix this one? Well, we're going to take another pair and we are going to share it. All right, so put that there and redraw. So now we have a triple bond and this is how it ends up. All right, so now you might see this more commonly drawn with the non-bonding electrons on top or maybe on side. That it really does not matter. All right, so this is still following our honk 1, 2, 3, 4 rule. Nitrogen has 3 bonds and 2 non-bonding electrons or on the atom. All right, so if you are starting to see this and you want to move multiple pairs of electrons in one step, that is fine. So just take your time. All right, one more to put in your notebook. Let's do a polyatomic ion. We're going to do carbonate. All right, so carbonate, that is CO3, 2 minus. All right, so let's add up our valence electrons. We've got carbon and 3 oxygens. So carbon has 4 valence electrons. Each oxygen has 6. All right, so let's see, what's that? 18, 19, 20, 21, 22. All right, 22 valence electrons. But remember, this 2 minus, that means that we actually gain 2 electrons. So we're going to add 2 more. So we've got 24 electrons to make the molecule. All right, so CO3, let's put carbon in the middle. All right, oxygen, oxygen, oxygen. Connect with single bonds. So we're from 24, we've used up 6. All right, so that is what, 18? All right, so then I'm going to sprinkle around 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right. Okay. So at first glance, it might be like, oh, that worked out pretty well. All my oxygens have an octet, right? Those look good. But notice carbon in the middle, it does not have an octet. Carbon does not have 8 electrons around it. It only has 6. So we are not done. Now, here's the question, like, which pair do I move? Well, it doesn't really matter. So just pick any pair. All right, I'm going to grab these ones and scoot that down. Now I'm going to redraw. All right, so oxygen, double bond, pair, 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 carbon, oxygen here, here, and here. Okay, you could have easily have grabbed a pair of electrons on the oxygen on the left or maybe the oxygen on the right. That doesn't really matter as long as I am meeting the octet rule. All right, so let's see. This oxygen has 8. This oxygen has 8. This oxygen has 8. And this carbon also has 8. All right, so that is our final molecule. All right, and then that leaves us with one last thing to talk about. So this example, the fact that I chose these valence electrons to move and turn into a double bond when I could have easily have chosen electrons on a different atom, well, that means that this actually has something called resonance. That means it has more than one correct Lewis structure. All right, so valid Lewis structures that differ only in the arrangement of the electrons. All right. These are, for all intents and purposes, like the same molecule. They have the same energy most of the time, sometimes. And some, okay, maybe that's not true. So some of them are more favored than others. But, like, for instance, in this example, if I had moved another pair, it would not have looked any different. It would honestly just look like I rotated the molecule to the side. So all of those versions of CO32 minus have equal energy. They are identical. We couldn't tell them apart unless we could mark the atoms themselves with like a radioisotope or something. All right. So there's quite a few things that have resonance. I'll just do a quick example here. I'll just do the same thing with carbonate. So we had C, we had double bond O, and then O and O. And yeah, I'm drawing it a little bit different here. So this is actually something that comes up a lot in organic chemistry as well, where you're kind of moving or pushing electrons around. So I could say, okay, well, let's take this pair and turn that into a double bond. But then this double bond, that can come up and become a lone pair. So then I redraw it and I get oxygen. This one here has the single bond. Dun, dun. All right. So that's one resonance form. All right, I can do the same thing. I can say, well, let's take that pair of electrons, let's move it back. Oh, wait, no, that's not what I want to do. Sorry. All right, so same thing. I could take from the other terminal oxygen and push these electrons here and then push these back and redraw. Two, three, four, five, six. 1, 2, 3, 4, 5, 6, and 1, 2. Okay, so these are sometimes represented with these double arrows here that I have in the middle, because you can kind of imagine like that the molecule is kind of in the state of flux. The electrons can move around in between these oxygen atoms, and their like average location is the picture that we draw sometimes. All right, so that is resonance. All right, so I am going to leave you with a few practice problems to do on your own. Okay, so you can check these in the slides when you're done. I'm not going to do them on the screen. You can do them in your notebook or on a whiteboard and just follow those same steps, right? So we've got O2, we've got nitrate, NO3 minus, and then also its resonance structures. And O3, this is a different molecule. This is ozone. All right. So ozone, it's kind of an interesting molecule. It's a little bit asymmetrical looking. And then question, you don't have to draw them, but does it have any resonance forms? All right. So that is it with the notes. You don't need to upload a picture. I'm going to trust that you took these and did your practice. Your homework is a Canvas assignment. You've got 2 attempts, so take your time on it, draw out any pictures, and that is today. I will see you guys on Wednesday.